Hi everyone, Big Mac here. Grab your pencils because we are going to go over some of my favorite Calculus 1 questions. What are we talking about? Well, this last semester I had the honor of teaching a first semester calculus course. And in that, in doing so, we had, of course, the textbook material, but I got to write the exams, which I found, very exciting in that sense. That way I was able to try and figure out what I thought was important through the class, and hopefully the students would, obviously, hopefully I would hope that they did well on it, but just wanted to get an idea of where they were at, what they understood, how they understood. So, a couple things here. The way I'm gonna have these particular questions laid out. As far as I can think of, I came up with these questions myself. So, these are, it's hard to copyright question material because, you're just like switching numbers around and stuff, but if by any chance you want to use one of these questions, feel free just to let me know, first of all. Of course, of the questions that I'm going to be listing here, there's just a couple of them. They're meant to represent kind of the broad spectrum of the material that is covered in a first semester course. In terms of solutions, that'll be in another video. If you want to try and leave solutions on the bottom, or if you want to try and work on maybe a couple of these problems or not, for yourself, go ahead and leave it as a comment. Don't give too much detail. Like don't write out your solution. Just say like, oh, the answer's 15 or something like that. That way, other people might be able to see if they come up with the same answer or not. So the general format that that was me hitting stuff. The general format that I'm going to be doing for this section is I'm going to just say, what exam it came from, what basic material was covered on that exam. I'll describe the question. I'll then emphasize whether calculators are or are not allowed for that exam, because some exams I allowed calculators, some I didn't. One exam, part of it was allowed for calculators and part of it wasn't. And then my estimation of how long it should take a student to finish that problem, or pretty much how long I allocated it during that time. Alright, so number one. The first exam was a pretty straightforward pre-calculus review, so I actually had a couple of multiple choice questions on this exam. These multiple choice questions turned out to be somewhat difficult. So here's the first one that I have. How many solutions are there to the following equation? 2 equals 3 plus 2 cosine of 50x, where x is in the interval between 0 and 4 pi. So you have your options there: 0, 12, 50, 100, or none of the above. Calculators were allowed on this question, and the way I had everything planned out, I hoped that students would be done with this question in about 3 minutes time. If you want to try and work on these problems, maybe give yourself the suggested time, see how long it takes you otherwise. Feel free to pause the video too. I'm just going to be going through these pretty quickly right now. Second question from my pre-calculus review, again, kind of surprised me what people were picking in this situation. But if we had a function g of x, and we know that the point 5 minus 3 is on the graph of this function, which of these points must be on the graph of the function y equals negative 2 g of 5x? We have the points minus 1, 6, 1, 6, 25 minus 6, 25, 6, or 1 and minus 6. Again, this was all part of the first exam, so calculators were allowed, and ideally students would finish this problem within 2 minutes time. Starting with the second exam, the intro to the derivative, we just talked about, some basic stuff. Introduced the limits, introduced the definition of the derivative, did a couple of basic examples of it by that time. So here's one question that I had from the exam that I found really informative. Find all values of capital B and capital K so that the following function is both continuous and differentiable at x equals 1. So for x being less than or equal to 1, the function goes by bx plus k. And for k being greater than 1, it goes by k squared x squared. So of course this is a piecewise function. So you may have to try and figure out what values of b and k will work for these things. In particular, I'm looking for specific examples like, oh, b is -5 and k is 12, something like that. On this problem, on this exam, calculators were not allowed, and ideally students would finish this one in about 6 minutes time. Then this is another question from exam 2, a little bit longer. It's got 4 parts to it. So obviously I gave students a lot more time to work on this one, 10 minutes. Some parts of it were very straightforward, other parts not so easy. So suppose capital G represents the gas efficiency of a vehicle as a function of the velocity v, or basically the speed of the car, where the units of G are in miles per gallon and the units of v are in miles per hour. So depending on how fast the car is going, that'll determine its gas efficiency. So a couple obvious questions. 1, what are the units of dg/dv, the derivative of g with respect to v? Part B, give a practical interpretation of g prime of 40 equals 1. You know, what the heck does that even mean? And then part C, suppose we know that g prime of 40 is 1, g prime of 61 is -2, and that g double prime of v is constant. Given this information, determine the speed that maximizes the fuel efficiency. Going back to exam 3 now, we talked about more properties of derivatives, so we talked about derivatives of more kinds of functions, as well as we started introducing notions of optimization and other things. So here was a section of true-false questions that I put on the test. In terms of time allowed, about 2.5 minutes per problem. Maybe you'll need less time than that, hopefully. But that was what I allocated basically for the exam. So the first one, if a function f of t has a local maximum at x equals a, then f minus 1 of t, hopefully you know what that represents, has a local minimum. The second one, if we know that the derivative of a function, g prime of t, is between 1 and 2 for all values of t, we're also given the initial value that when t is 0, g is 2012, then it's possible that g of 2012 was 5555. That's a very nice number. Is it possible for that to be true? And then the last case, if a function, completely different function, f of x, has a local maximum when x is 2, then we also know for a fact that it has to be the global maximum in the interval of 1.99 to 2.01. So since we have that maximum there, then it's obviously got to be the global maximum in between this very small window. True or false? This is the other question that I had from exam number 3. Again, we talked about different kinds of functions. So we had the following function. We had the hyperbolic cosine squared of x, and then minus the following quantity, e to the x minus e to the minus x all over 2. That whole thing squared. So again, calculators were allowed on this part. Question was, find the derivative of this thing and simplify as much as possible. Ideally, I gave students would solve this problem within 3 minutes time. Some students took, looking around the classroom, some students took 10 minutes on this problem. Some students took 10 seconds. Finally, the last problem that I'll be talking about in this video, part of the last midterm that I gave in the class, not the final, I didn't write the final at all, but using applied derivatives and integration. So we talked about different ways to, use the derivatives, things like L'Hopital's rule, related rates, that kind of stuff. And then also basic properties of integration, summing, left-hand sum, right-hand sum, antiderivatives, those kinds of things. So this was a very long problem, so I actually broke this exam up into 2 days. And so for this problem, I estimated that students would use hopefully 15 minutes of time. So here's the following setup. We have a large hollow cone with a square base, aka a pyramid. We turn it upside down and we fill it with water. The total dimensions of the pyramid is that it's 30 feet tall, and the length of the square base is 20 feet, as seen in the little picture that I redrew for you guys. So, like I mentioned, it's hollow. We're adding water to it. We are adding water at a rate of 48 cubic feet per minute. So the fact is we know how much water we're adding, but how fast is the height of the water changing when we have 1,337 cubic feet of water? Yes, it's leach feet. I tried to be cute. Nobody called me out on it. I was kind of surprised on that. So the question is, we know how fast the water is getting pumped in, but how high is the height of the water changing, knowing that we have this particular, that we are inside this pyramid shape? So that's the question here, and for anybody who wasn't sure, I also did give the volume of a pyramid as, 1/3 base squared times height. Again, this is just a regular square pyramid. All the lateral sides are the same, so nothing weird in that sense. So like I mentioned, in terms of comments, go ahead and if you guys want to try and post solutions, sorry, feel free to do that. I will be posting answers sporadically. I haven't decided how to do that yet, but keep looking forward to that. So until then, this is Big Mac saying, later.